Hi everyone, my name is Raven. You probably know me from your chemistry and biology classes. Today I'm going to be going over the Lewis dot structure. I know we've gone over a lot of things like stoichiometry that we're probably going to have to review, but we've got a request for the Lewis dot, so we'll start there. So first off, what is the Lewis dot structure? The Lewis dot structure is a structure kind of similar to the empirical formula that helps you determine not only what the atom or the molecule it's composed of, but it also helps you determine the shape. So let's look at this. Let's go really simple and start with water. Obviously, we know there are 2 hydrogen, 1 oxygen. But what does that really mean? When we look at it this way, we can determine that, if you'll excuse me while I'm writing this is probably a little off, but let's just go with it for now. Can't remember it off the top of my head, and I don't want to start doing it in front of you guys until we get to the equations. We can tell, utilizing this electron here, that it is a bent shape, similar to this. We can then determine polarity using this. So this is really helpful to chemists. I'll explain why in a little bit, but this is really more things that we have to learn a bit more before we get into. So, it's really important just so, again, we can determine electronegativity, and just see how helpful it is. When I brought up water, this is actually one of the properties of water, and it's really, really important. So remember that water is a bent molecule, but that's something we're talking about in the future. So for now, just store it in the back of your brain. Okay, so you may have noticed this partially done periodic table down here. I kind of already did this once and messed up the end of the video, so that's kind of why my 4 hours of work have gone to waste with this section here. But we're completely ignoring it. Don't care about the transitions, or excuse me, the you know what I'm trying to say. It's been a long day. We're going to completely ignore this section. So we're sticking with the main group here, which are 1, 2, 3, 4, 5, 6, 7, and 8. Why are we doing this? I want you to grab your periodic table. I'll give you a few seconds after I finish talking to do this. Grab your periodic table and grab a pen. I'm going to stop talking now for about 3 seconds so you can pause your video. Alright, so assuming you have a periodic table, I want you to do me a favor. I'm actually going to grab a different color here. I'm going to grab black. And I want you to label your periodic table, starting with hydrogen. 1, 2. Skip all the way over to the remainder of your main group, starting with boron. 3, 4, 5, 6, 7, and 8. Right now, other than helium, I want you to completely cross out 8 and put a 0. Helium is our only exception in our noble gas group. So kind of circle helium, do something to indicate that it's an exception. Now, why did I have you do this? Professor has showed us a way to figure out valence electrons, and it's definitely close to that. So I want you to figure out, utilizing Professor Hess's way, how to do it. Okay, since you did that, you're going to figure out that the answer is the exact same as the number I gave you. Our only exceptions are radon and helium, but that's just something you're going to have to memorize. Otherwise, this is a really good method to remember the valence electrons without having to do a lot of math or work. So, as you can tell, if I said how many valence electrons are in lithium, you go, okay, lithium's a metal, okay, lithium's right there, go all the way up, oh, there's 1 valence electron. If I said carbon, go up 4. So you don't have to do any math, you don't have to do any hard thinking, you can just go straight up and go, oh, it's 4, it's 7, it's 6, it's whatever. This is accurate 100% of the time, other than those 2 exceptions I mentioned. So just take a nice breath. This is something to save you time on your tests. Because we have not been told really how this was determined, don't worry about doing it on the test, just use this method. Alright, so great tip and trick there. Now it's time to move on to the octet rule. And the octet rule is amazing. So, I'm going to be using X. Actually, let me grab blue. I'm going to be using X for our atom here. So this is a standard atom. Some atoms are not like this. But, I'm going to use the X. With the octet rule, it says that we have 8 electrons, regardless of the atom. There are exceptions, but I'm not going to get into that yet. So that means that all electrons are written as either X with 4 dots around it, 8 dots around it, or X with 4 lines. I personally prefer the 8 dots, and then only using the line when there's a bond, or preferably a double bond for me, or more. But it's all up to your preference. For this video, I'm going to be using the dots and the lines only with the bonds. So most of ours are going to look something like this. And in this scenario, these atoms, whatever they are, follow the octet rule. When it comes to octet rule, and this is kind of skipping ahead to geometry, you see how I have only the 2 electrons here? This is saying that these 2 share. So these 2 share it, and these 2 share it. So really, even though it looks at first like there are less, there are less, but these are sharing them. So rather than having 16, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But I'm getting ahead of myself. Just remember that I'm going to be writing it looking like this. That's all you need for now. Going back to the octet rule, you really don't need to know how or why it's written like this. That's something I'm sure we'll get into later in class, and I'll bring it up as soon as we need to. But just remember, X, being that atom, always has 8 electrons. I'm going to let you pause your video here to write notes. So I'll stop talking for about 3 seconds. Alright, so just to recap, octet rule means there are 8 electrons in everything. It can be written either this way or this way. I prefer writing it this way. Alright, now let's go into the exceptions. So far in class, we've really only gone over boron, Be, which I cannot remember right now, which I'm a very bad teacher, and sulfur. Each of these can only fill a certain amount, and I'm going to go over with you in a few seconds how to determine how much they can fulfill. But for right now, I'm going to show you how the exceptions are written. Because we're just talking about exceptions, I'm going to write it as A instead of X. So right now, X is our normal that follows the octet, and A is our exception. Everyone with me here? Alright. So, if we have 1 electron, we're going to have 1 dot above. In all reality, you can write this dot wherever you want. You can write it here, here, or here. Really doesn't matter. But some teachers are a little particular. So for now, if there's only 1, write it at the top. If we have 2 electrons, you're going to write it here and here, or here and here. looks like my light is kind of hitting it, so there's my shadow, as you can see, above and to the side. All right, let's look at 3 electrons. Some teachers are a little particular about this one as well. So we're going to put it 1, 2, 3. So if you can't see that, it's the left, right, and above. You can also kind of change this one up. I wouldn't suggest it. Okay? Next one. 4 electrons. There are a couple ways to do this one. I personally suggest for this class, 1 in each corner. Not corner, side. You can have it so that they're adjacent to each other, not adjacent, opposite of each other. Would not suggest it for this class. And I will get to you about that if you ask in the comments. Otherwise, not going to get into that long spiel. Alright, we have 5. Oops, my bad. You're going to do it like you're imagining. 1, 2, 3, 4, 5. You're going to have 2 in one area. Really doesn't matter. This one teachers are less particular about, so just do wherever. So you're going to have 1 on each side, and then you're going to add a second. So you're going to have 2 in one area, 3 in the other third. 1 in the other 3, excuse me. 6, you're going to do something very similar. 1, 2 above, 1, 2 to one side, 1 and 1 to the others. And then, if we're talking 7, 1, 2 above, 1, 2 to the side, 1, 2 to the side, and 1 under. Not very difficult, right? So, I'm going to erase this after you guys have a few seconds to write it down, so I suggest pausing a few seconds. And then I'm going to ask you a question. If you don't get it, talk to me, put a comment, something, and I'll take care of it for you. So write this down. Really important. All right. If you haven't written it down, I suggest pausing it because I'm going to erase it. All right. Now I have a question. If we're going to say this has 1 electron, what would you write? If you wrote something like this, that is correct. You can, like I said, write it like this, or this, or this. But remember, again, some teachers do not like that. This is just going to save your rear end in the future. So trust me on this. Don't write it like this. I'm sure Professor Hess will not mind, but you never know. So, we've gone over how to draw them. So let's say sulfur had 6. You do an S. 1, 2. Gotta write those circles bigger for you. 3, 4, 5, and then another one wherever you want. Probably here. No big deal. Pretty dang simple, right? Remember, he does follow the octet rule in this class. So except for those, probably those 3, there are a couple others, and there are a couple rules that I will bring up later if he wants us to. Because there are 3 rules, 3 exceptions to the octet rule. That's only one of them. So if he wants us to go over that, I'll make another video on it. If not, then we can just leave it alone. That's probably a 102 or 111 concept. Alright, here's the part where a lot of people have issues. The geometry. The geometry is a lot simpler than it sounds. You saw how I went like like that earlier? Yeah, that's all it is. It's really easy. But let me show you how to do this a little slower. I'm going to start off with something completely new to me. So you and I will be doing this at the same time. All right? We're going to assume this will work well. In, 2, F2. So, utilizing what I taught you down here earlier, I want you to tell me how many electrons are in that. Or I want you to figure it out. I'll give you 3 seconds, pause your video, figure it out. All right. If you said that your electrons equal, let's see, 5, 10. All right. If you said it was 24, that's what I got. You could tell because you would go 5 plus 5 plus 7 plus 7. So that's 14 plus 10 equals 24. So how would you work with this? And again, I'm assuming these bond well. So let's do nitrogen and fluoride. So nitrogen will look like let me actually change color for this. Nitrogen will look something like N equals N 1, 2, 3, 4, 5, 6, 7, 8. So you're going to have 2 of those. And I want you to draw out every single solitary one of these. These are going to be individualized. So you're not going to connect any of these yet. So again, N equals N 1, 2, 3, 4, 5, 6, 7, 8. Again, I do want to tell you that if you write it like this, that is correct. So don't freak out. You're doing it fine. As for fluoride, let's do a different color. And this one follows the octet rule. Should have fluoride with 8 electrons. Doing good? So in class, we learned about which ones have the better receptors. Electronegativity would tell us, we're going to go this way. Electronegativity tells us nitrogen would be our central atom. In this instance, we don't have a central atom, but that's fine because we do have 2 nitrogens. So that's perfectly fine. We're going to start working over here. So we know fluoride. Let's see, is that coming through well? No. Oh, that one stinks too. All right. So we know that nitrogen is going to be our central atom, or central-ish. And then fluoride is going to be on the outside. We have no idea if there's going to be a kink, if this is linear or what. But we're just working with this for now. It's cool. I want you to redraw your atom. So they're not connected yet. You have fluoride, nitrogen, nitrogen. That's not fluoride. All right. Nope, I'm good. So we're working with these 4 right now. They're unconnected. So what are we going to do? I'm going to erase this portion. Just remember the chemical equation, it's fine. And I'm going to move this away. E equals 24. So what do? To connect these, we're going to have to bond them. Right now we have 8, 16, 24, 32. That's way too many because we only want 24. So, for this, we're going to bond them. These two. This one up. Okay. These two, and these two, well, they both have 2. So what we're going to do here is we're going to bond these. It's going to be pretty easy. All you're going to do is have F, and you're going to fill the octet rule with the F. N. Well, if we're binding these, we already have 2 right here. We're going to keep it so these 2 share. And that's kind of called a covalent bond. What this covalent bond does means that this is sharing. So if I fill this with 6 more electrons, well, look at what happens. So we have 1, 2, 3, 4, 5, 6, 7, 8 for this one. But we have 1, 2, 3, 4, 5, 6, 7, 8 for this one. So what Professor Shaskus was trying to show us in class today, or a couple days ago, is that this is shared between the 2 of them. And that's what creates our bond. You may see it written as something like this. And that is the exact same thing. If you have any questions about this, talk to me in class or write a comment. Again, I know I'm going through this pretty quickly, but this is something it's going to take a long time to explain over a video. So if you don't get it, talk to me in class, whatever you need. But the only thing you need to remember is this is shared between these 2. So this one, without this, if I just cut this off, first off, that doesn't fit the octet rule. Secondly, this one will just fly away and do its own little thing. So these 2 share one. This is the exact same thing as these 2, just it's not bonded. Alright, I'm going to erase this so it makes it look a little nicer. Okay, so I'm going to rewrite it. What do we do next? If I am trying, hold on, let me actually write a line here so that you know different. If we're trying to bond this one to this one, we're going to do the exact same thing. Going to have an N. Now my question is, does this fulfill the octet rule? And it does. We have 2, 4, 6, 8. 2, 4, 6, 8. That's all you need. So remember, right now, we have these 2 sharing this one, and these 2 sharing that. So currently, we haven't gotten to our final molecule, but we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now, let's get to the final one. So, we have these 2 sharing one. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So E equals 28. On this one, let me recount what we had. 8, 16, so we had 32 here. Just by having these ones share something, we already made it a lot nicer looking. But right now we need to get rid of 4 electrons, or reduce it by 4 electrons. So I'm going to go down 1 more. I'm going to erase this because we're good. Don't need it anymore. And I'm going to use this section right here. So currently we have Excuse me as I rewrite this. Okay, so this is what we currently have, but it still has 28 electrons. So what can I do? If I change this up a little bit, we can drop it down to 24. But how do I do that? Well, here's a really good way. So I'm not even going to pay attention to any of the electrons. So F, N, N. Let me make sure that's big enough for you guys. I'm going to make that a little bigger. F, N, N, F. We're not going to care about anything right now, except for these bonds. Let me erase that and do a different bond. So we're going to ask ourselves in the future, can these be double bonded? And for now, yeah, they can. Actually, they can, period. So, where would you think a double bond would work best? Well, right here, we could only make one double bond. But here, we could make two. Additionally, this will help keep the molecule uniform, because what we want is uniformity. If we had two double bonds here, it'd make the atom look something like that. Looks weird, right? Doesn't look like anything we've seen. But if I did a double bond here and here, it will look something like this. Same thing, it just looks a little more familiar with what we've worked with. Okay, so let's start thinking. I'm going to add the other bonds in. Okay, after I finish writing this, I want you to go ahead, go to town, try to figure it out. I'll give you 3 seconds. Feel free to pause the video as soon as I stop talking, and you can figure this out, okay? All right, go ahead, pause the video. All right, so let's look at this. You have 28 electrons, and you need to go down to 24. So, how are we going to do this? Well, we have both these two need to stay somewhat the same. Obviously, they can be changed, but if I removed something from either of these, if I moved something here, it's going to cause some issues. And I don't want to break the octet rule here, because if, say, I changed, let's say I changed something here, I would need to change something here. Obviously, that would affect this one. So, let's try removing these and creating a double bond here. Now, why did I create a double bond? First off, this is basically trial and error. It's okay if you get something different than I do at first. But I removed the double bond, or I removed these two and created a double bond here, because this is what a double bond looks like. So, what I just did, I changed, I'm going to erase this and try to show you. I moved these and brought them over here. It's still the same atom, still the same atom, just looks a little different. Okay, so we have 2, 4, 6, and 8. Remember that this line, a line, equals 2 electrons. So right here, I have 4 electrons. Everyone with me? If not, post a comment with the time. I'm about 30 minutes in. So just post a comment with the time and tell me what part you don't understand. So we have 2, 4, 6, 8. Now we have a problem because we have 2, 4, 6, 8, 10. So what can I do? I can absolutely eliminate this. Now look what happens. 2, 4, 6, 8. 2, 4, 6, 8. Now let's count it out. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this matches this. We have 1 double bond, and this matches. If I were to have changed this, I could. That's the benefit of all. So let's try changing this. It's going to work, but let's see how it changes it. So let me move back to blue. So we have this. N. N. And then F again. So if everyone can see that, yep, looks visible. Let's go. So I want to change this into a double bond and take this away. So we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10. So we now have 10 on this one. I can eliminate that though. So what do I do now? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Now let's count how many we have. 1, 2, 3, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we have 24 just by adding the double bond right here. So we have something that looks kind of like this. Excuse me, let me actually write that a little higher up here. So this one looks kind of something like that. And this one looks kind of something like that. They're both right. But how in the world are they right? This is called resonance. Resonance is when 2 molecules, this identical molecules, are correct. Even though, have different structures, they're both correct. Neither of them's wrong. They're just different. Now what happens here is something, I actually don't think there's a name for it. But what happens is that in all reality, this is not the correct one. This is not the correct one. It's correct when we write it out like that. Yeah, this is how it looks in real life. But the correct version is something an average between 2 of these. So let's think of it like bunnies, or like children actually. So the average family has 2 to 3 children, right? But in all reality, the real version, the way we look at it in math, is a family has roughly 2.5 children. Obviously that can't exist. You can't have 2.5 children. But the way we look at it mathematically, you have 2.5 children. So when we're looking at this mathematically, it's something between this and this. So even though it can't exist in real life, it's kind of almost identical to that children example. It's a little funky, but just know for now that either of these are right. So I'm going to give you a few examples, and then I'm going to walk you through them. I should have warned you that I was erasing the board, but if you need to, you can just rewind the video. Try not to erase that. Okay. let's look at, we've worked with carbon dioxide before, so the first example is going to be CO2. I want you to try this on your own. I'm going to give you plenty of time. Well, you can pause your video, and I want you to do this. Then we're going to do it together. So I'm going to stop talking for 3 seconds, and you pause your video. Alright, first thing we're going to do is determine the electrons. So electrons equal what? So first we're going to go down here. Carbon is 4. So C equals 4. And oxygen equals 6. Because there are 2 oxygens here, we're going to multiply that by 2 and get 12. 4 plus 12 equals 16. If you got that, you're on the right track. Now, we're going to write this out exactly how we did the former problem, the N2F2. Okay, we're going to have carbon. We have one of these. Let me write this bigger for you. And I'll write this in a different color. So we have carbon. And then 2 oxygen. Remember, these all have to follow the octet rule. These are not any of the ones I mentioned formerly. Okay. Oxygen is not going to be our central atom. If you have oxygen as a central atom, you need to go back and look over, because oxygen is less electromagnetic. Remember, nitrogen, carbon, and stuff like that, you're going to want those as your central atom. So, let's go back. Fair warning, my video looks like it's about to go up, so I'm only going to do 1 or 2 more of these after this. If you need more, I will post more. I will make a Word document, and I will probably a Google document, and I'll put it in the description. So, we're going to start this off. We have our C. And remember, we're going to have these 2 shared because we need them bonded. So we have O is bonded with C. And then O again. If you do not have this, if you do not understand this, go back over. It's around 30 minutes. Go back over and do this again. It's going to be worth your while. If you don't understand it, leave a comment or just talk to me in class. Text me. You guys have my number. It's okay. I won't judge. So, at this point, we have a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have 20 electrons. How are we going to reduce this? Well, we could always take this away and create a double bond. Personally, I think that's the right way to go. You could also have done it from this end. Either one's fine. It's all good. I'm just going to move from this end because it's closer to me and it's a little easier. I hate reaching over the whiteboard. It's easier. So, I'm going to take my O. Oopsies. I'm going to take my O, so my oxygen, and I'm going to have it where I eliminate this section. I'm going to move this over here. Alright, everyone with me? So now I have a double bond. And remember, this is 4 electrons. And I'm going to have my carbon. And then I'm leaving that second oxygen alone for the time being. I may or may not have to change it. I don't know. That's something I'm going to have to figure out later. So, right now, I have a total of, just throwing this away, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Simple as that. If, say, this was CO2 -2. Because remember, every time you have a -2, you subtract 2. Or, excuse me, you add 2 to the electron. If it was a +2, you subtract 2. So let's just pretend it's a CO2 -2. So instead of having 20 electrons, or excuse me, whoopsie daisies, never mind, let's ignore that. For some reason I thought we needed 20. So right now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Wait a minute. 2, 4, 6, 8. Oh, I skipped a step. See? I completely understand this, and I skipped a step. This is why you always double check, because even I skipped a step there. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But our carbon does not follow the octet rule. So what we're going to do is we're going to erase a set. So now we have 2, 4, 6, 8. See, if you caught that, you're doing better than me today. I'm tired. Don't judge. So now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. This will get repetitive and annoying as can be. But it's worth it. At the end, it's your grade's going to be worth it. So right now, we're at 18. So what do you suggest we do? If you suggested taking one away from the oxygen and adding a double bond to the carbon, you would be right. So let's do that. Oops. So let's see how many we have. 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, why do we have that? I want you to tell me. Well, I want you to guess. If you suggested that the carbon did not follow the octet rule and we need to eliminate 2, you'd be correct. Because at that point we had 2, 4, 6, 8, 10. So now with this, we have an oxygen with 4 electrons. Well, 4 additional electrons. A carbon with only the double bonds connected to it. And the oxygen back again. You would be correct if you had that. Remember, this is only one way. I do not believe this one has a resonance, but if it does, and if you had something similar to this, and they all followed the octet rule, you may have been correct. I personally would suggest going through these again and doing these steps, seeing if you got it, as this is the most correct answer. But, again, everyone does it a little differently. Personally, try to stick in this manner. And again, see, everyone makes mistakes. We're just going to double check again, just to be safe though, because I don't want to tell you something wrong. So we have 2, 4, 6, 8, 10, 12, 14, 16. Our total electron count was 16. This one has 16. So this is your correct answer. If you can't see that very well, I'll write it again in black. And once again, if you write it something like, I really don't have space. If you write it something like this, remember, Professor Shaska said he really doesn't like that, but it is correct. I'm going to do one more. And remember, this may not be correct. Well, this may not occur in nature, naturally, but whatever. It's good practice. Let's try something with sulfur. So, let's see. So, how many atoms does lithium have? So, lithium has, in their valence shell, 1. Multiply that by 2, you get 2. Sulfur, in this case sulfide, has 6. So electrons, you have 8. So we're going to try to get something with 8. But you have 3 atoms here. It's going to be a little weird, right? So we're going to go for the sulfide in the middle. Actually, let's try this. Lithium follows the octet rule. Sulfur, we just don't know. Well, you'll know after you figure it out, but you don't know yet. So, we're going to write it with sulfur in the middle, as it's pretty dang electromagnetic. So all the way over here, lithium's all the way over here. You're going to want to put sulfur in the middle. And then it's blue, it's not purple. So we're going to have lithium. For right now, we're going to do this. So, having sulfur with only 4, we have 2, 4, 6, 8, 10, 12, 14, 16. Gonna make sure that's right. Yep, 16. So we're going to assume that sulfur needs something like that. So, let's work with this. Let's go. Well, I'm gonna let you try this. Go for it. Alright. So, we're going to move lithium. We're going to try to make a double bond here. I'm going to make a line there. So, remember what we do here. We move this one over. So, we have our lithium. So that's 4 electrons there. And do not write this on your test. You're going to regret it. Do not write this on your test. He will dock you. Sulfur. Actually, let's not do that step yet. And you can absolutely go ahead of me. So now we have 2, 4, 6, 8, 10, 12, 14, 16. Wait a minute. 2, 4, 6, 8, 10, 6. You see, even I get stumped sometimes. Okay. Let's look at this again. 2, 4. Let's move this one here. This one may actually be one that we're going to have to talk to. Oh, it doesn't occur naturally in nature, that's why. Okay, well, in instances like this, it actually doesn't occur naturally in nature, so there's no actual correct answer. That was my bad. But again, you can kind of see how that happened. Because these two just don't occur naturally in nature, they're not going to really work. So, my bad. Either way, good practice on this portion. I know what I was trying to do. So for now, I'm actually going to, because it is very close to my phone being done, I only have about a minute and change left. Minute exactly, actually. Alright, I'm actually going to create a Word document with questions and a key. And I'm going to put it in the description. It should be there within 24 hours. If not, let me know. Send me an email at ravenmachie@mycwi.cc. Or you can send me a text, either one. You will know me. Feel free. And thank you for your time. If you have any questions, let me know. I am not a jerk. I will answer them as honestly as I can. Alright? Thank you.